So welcome to today's customer success webinar. Thank you for joining us. There's some more people entering, but we're going to make a start. Today we are delighted to host DGT Associates, Surveying and Engineering. DGT are New England's premier surveying and engineering firm. They provide a full catalogue of services to a variety of stakeholders, from developers and construction to municipalities and homeowners. They have a history, dates back to 1877, so their clients' projects, they are certainly in safe hands. We are going to quickly run over some Zoom rules so you know where to find things and what's going to happen. So all the participants will be muted. We have a panel in the background, okay, which are from Kontur and DGT. And if you want to ask a question, use the Q&A functions located at the bottom of the webinar window to ask questions. We're going to try and answer your questions live if possible, if it fits into the presentation, or we'll answer them by typing a response to you. All of the participants can see your questions and the answers, okay? And if we don't get to your question today, we'll follow it up afterwards, all right? So our presenter today is from DGT, of course. It's Mitch Liddell. Mitch is a geophysicist. He has extensive experience in electromagnetic and tomographic methods. He's joining DGT in 2020, and he oversees all data collection and analysis. My name is Paul Collins, so you know who is talking to you right now. I'll host the webinar, okay, and I'm the Kontur's technical sales engineer. So let's hand over to Mitch, and I hope you enjoy the webinar. Okay, Mitch, all yours.
All right.
All right.
All right, everybody can hear me? Everything's going smoothly at the beginning?
Yeah, I gotcha. Looks good.
Good stuff. Okay, yeah, thanks a lot to Kontur for hosting this. I appreciate the opportunity to give this talk. What we're going to talk about, or what I'm going to talk to you guys about today, we're going to talk about utility mapping. First of all, a little bit of a history of utilities and how we got to the modern state we're in with our utility infrastructure, how maps are useful and indeed necessary for how we deal with modern infrastructure issues with utilities. And then how we use GPR to augment how we do traditional utility mapping, because of course utility mapping was happening before we had any GPR. So first of all, I'll give a short history of underground utilities. It's older than you think. Like, we think about our modern cities, but ever since we've had civilization, we've had issues with utilities. So an example here from the UK and from ancient Greece. I mean, these people putting in their utilities, they had to think about where they were going to put them, and maybe they had to repair them and replace them at some points too. So utility mapping, this is an ancient, fairly ancient industry. From the modern perspective, there was a big boom in the 1800s. This is sort of where we can begin the trace of our current industry. And there's a lot of public interest in this too. You can see this is the cover of Scientific American in the 1800s, people thinking about how we're building our modern cities and how we're using infrastructure to make our lives better, to have utilities available to us wherever we need them. So we began building these enormous infrastructure situations all over our modern cities. So this issue where we have really congested streets underground, it's not just a modern issue. This is an issue that happened right off the bat. We were filling up our space, filling up our streets very quickly. And accompanying these utilities, these new utilities we were building, were really nice detailed maps. Now this one is so nice, to be honest, I would put it on my wall. This is a sewer detention system. But the detail and kind of love that goes into these sort of maps, this is something that we kind of have lost today, actually. But we can look back on our kind of forebears in the utility mapping industry and really appreciate the work they've done. Of course, the first thing that happens after you build an enormous amount of infrastructure is that it starts to age. And so we have to deal with repairs, replacements, and new utilities. So either we're going to take out the old utilities, put in new ones, or maybe we abandon them in place, put in new ones. We have to know where everything is so we can do this. So utility maps were extremely important. We need accurate maps so we know how to move forward with this. And this issue we have even from back in what is this, 1895, the Boston Transit Commission. They're thinking about over 100 years ago how we need accurate maps to be able to move forward with our utility infrastructure.
So this is the
Yeah,
beginning of 3802 or PAS 128
yeah, basically,
from
like they're saying
1895.
there's enough need in 1895.
Mm.
The problem is known. It's a big enough problem back then that they have a commission to figure out, like, how are we going to do this? And what they noticed was the accurate records, these accurate maps, they either don't exist or they were lost in a lot of cases. Not in every case, but in a lot of cases. So kind of have to reinvent the wheel over and over again. And this is an old problem, and we have to invest in new locating and new mapping over and over and over again. Yeah. So that brings us to subsurface utility mapping and how we address the problem. So not all maps are created equal. On the left, you can see a map. This is a fairly simplistic one where basically what we've done, or what someone's done, is connect the dots between manhole covers and gate valves. It's not super accurate. I think if I sent you out with a backhoe and said, please go dig for me, dig a hole and try not to hit a gas line or an electric main, I think you'd want to use the map on the right. So not all maps are created equal. We have to be accurate. We have to strive to be as accurate as possible. So we can have accurate maps either in 2D or in 3D. This is an example of, I want to play the video here, I guess. I have to click it. This is an example of how we sometimes can use 3D rendering to show very complex utility infrastructure in certain areas. So it shows you that it's not simple. Since the beginning, we've had these very complicated infrastructure situations and building on as they go through the years, building up on each other over the years. And it's not simple anyway. It's not just connecting the dots. And the costs are really great if we get things wrong. So if we have errors and omissions, obviously the financial cost is enormous. I'm sure anywhere you are in the world, there's been a big engineering project that's gone cost overrun, right? It's kind of surprising when they don't go overrun. And a lot of that would be because they run into things that they didn't know. They have to maybe move a gas line, move something that they didn't realize was there. That comes down to poor quality maps that go in the first place. If they knew where it was there, then they would be able to put that into their original cost estimates. But it's not just a financial cost. So this is an example of a project from St. Louis, and this is a hospital in St. Louis. So what they found here was that there was a gas line right around the hospital that was actually unknown. It wasn't on the existing maps. So this is not something, it's not just academic saying, well, we didn't have the right maps and this is going to cost us a little bit more. We can't really be messing around with gas lines and hitting an accidental explosion near a hospital. This is serious stuff. So there are challenges to how we build up these maps. A major challenge is that the asset owners don't actually tell us when they put in new utilities. So you can see here there's updates on the different manholes and things like this for telecom companies, and they haven't been updated since 1998 or 1987 for the manholes. So there has definitely, I mean, I don't have to tell you, there's been infrastructure spending in the telecom area since 1998, enormous, right? There's tons of new telecom utilities, but we don't have them on the publicly available maps. So how do we get them? They're not just handing them out. It's valuable internal information. So we have to find a way to get our information somehow. So what we need is a comprehensive SUM program, subsurface utility mapping program. We have to start with the old abandoned pipes from ancient history, 1800s, and we have to include with them the new telecom utilities that aren't on any of the existing maps. And these maps have to reflect decades and centuries of history. It's not a simple thing to do at all. This is an interesting quote from Dr. Ray Sterling here that basically is saying would be nice if we had this fantastic technology, a geophysical tool that could identify all the utilities. Fortunately, technology doesn't exist, and it really doesn't exist, but we can kind of cobble together through what does exist a decent way to figure out a comprehensive SUM. So the current way that we do, or the traditional way that subsurface utility mapping progresses, is with EM locating and GPR, but like pushcart GPRs. So these are pretty frequently used, and they work reasonably well. The problem with the handheld electromagnetic devices like this is they're only good for metallic pipes or things with tracer wires in them. But so it's not everything. There's plenty of utilities that are in PVC pipes and things like that. And push carts are pretty good for those, but they have some other limitations we'll get into a little bit later. So we decided that we think that there's plenty of room for innovation in SUM. So the reasons we think that: we need to cover large areas and streets. There's tons of roadway, right? And it's not reasonable to be walking around with a push cart everywhere. It's just too much. It's not safe to have workers working in the streets, working in the travel lanes. and it's extremely expensive and disruptive to close down roads. So on the right, you see a picture from vacuum excavation, actually just the other day in Cambridge. So you can see this is right around MIT. There's tons of traffic that has to be diverted. The lanes are closed all day, and it kind of can be annoying if you've just repaved an entire road and we're digging a hole in it too. So anytime we can avoid those things, that's great. And there's room to be able to do that if we innovate in SUM. And another aspect that's driving innovation is that the demand for SUM data is increasing. So this is recently in Massachusetts. All new projects shall include scope and work hour provision for completion of level B data. So that means geophysical data. So how can we best respond to this? We already know that there's reason that we need to innovate, and we know that even from the government coming down, giving new laws, there's going to be a lot of demand for new SUM data. So how can we do this? Well, what we've decided is we need to deploy mobile mapping systems to be able to collect data at volume. This is a little video of our new Kontur system attached to our frame that we've got made, so we can deploy it off of our van. We can lift it up and down, and we can collect data at driving speeds. We've been able to do that. So we're going to get into that next. So this is how we map with our ground penetrating radar with our new Kontur system. First of all, I talked a little bit about the pros and cons of these sort of handheld systems. The pros are, look, the push carts are pretty good for what they do. They're versatile and they're accessible for anybody to kind of pick them up and run with them. And they allow you to immediately identify targets if you can see them. But there are major drawbacks that we've discovered too. We still use these, but there are still major drawbacks. So it's very slow because it's just up to one person walking, basically. Safety concerns in the road. Usually, not always, but usually it's a single frequency. So that limits with the GPR what you can see because you're only penetrating to one single depth at a time. It's just not reasonable for large scale collection. So if you're trying to respond to this directive that we need level B data for everything now, it's not reasonable to be just relying on these. So we're only getting one slice at a time. So if you want to just compare the speed of data collection, this is a sort of back of the envelope calculation, but taking into account that our Kontur has 24 channels and relating that to a pushcart, which is one single channel, in one day, we can collect the equivalent of what it would cost one person to walk for 10 days, to walk at 3 miles an hour versus, and this is when we're collecting at 10 miles an hour of driving speed, which is, we can actually drive a lot faster, but I did this in a conservative way, this calculation, where we kind of bumped up the collection, the quality parameters kind of almost to max quality, like I said there. So this is a really conservative estimate, but it would take at least 10 days for a person with a push cart to get the same amount of data, but it really wouldn't even be the same amount of data because, again, it's just a single frequency. And we consider multi-frequency broadband systems to be extremely important. And that's one thing that Kontur was able to provide really effectively for us. So the high frequencies, as we know, they resolve things near the surface. I like this example, not that you would need to use a GPR to tell you this, but it's accurate enough, or it's the fine details there enough that we can even detect the paint on the roadway telling you where the left turn lane is. Again, there's easier ways to tell where a left turn lane is, but it's just an example to show how accurate it is. And on the left, the low frequencies at depth. So this is a pipe that we're able to trace, and you can see in the cross section at 7 to 8 feet, or I guess starting at 8, going up to about 5.5 feet. It's a pretty deep utility for the soil that we have in Boston to be able to find this. So we can see both at the same time without having to use, multiple push carts or multiple frequencies. So just to underline the point one more time, with the single push cart, we're getting slices of data, so like slices of bread. The analogy I have in my head is that when you have a broadband system that's collecting 24 slices at a time, you're not just getting way more slices, you're also getting all these different types of bread, like you have rye and sourdough all at the same time. So it's a whole bakery.
Yeah, I really like that. I really like that, and also I'm hungry.
Yeah, exactly.
I have a question for you from Mark. Hey, Mark, by the way, it's about the 10 miles. So is it lane miles, or is it full carriageway, or is it
10 miles of collection per day? Yeah, so that would be lane miles.
Lane miles.
Yeah.
Cool. All right.
And I made that 240 miles of GPR data because it's 24 channels at a time. So I'm comparing a push cart where you're getting one slice. You really are getting 24 slices at the time. You know what I mean? So that's the comparison I'm making.
Absolutely. Yeah. And this
Yeah.
is a 3-dimensional volume that you collect in your driving direction. Yeah. Mhm.
Yeah. Well, it is. It's 24 channels that are separated by whatever it is, like 7 centimeters.
Mhm.
So it's effectively a 3D volume, and
Yep.
the way that the way that I like to set the trigger spacing is that it's all of these the trigger spacing is similar to the separation between the channels, so it is sort of a huge 3D grid, I guess, and then
Yep.
you get a 3D volume of data, which you don't get if you're just doing a slice. I know there are software systems that can turn those slices into an effective cube, but it's not happening simultaneously, and that kind of cuts back on the advantage where I said, like, oh, you can identify things immediately. You can't if you have to go back to the office and then make a huge cube of data that took you 10 days to collect.
Sure.
Yeah.
Gotcha.
Yeah. So I'll talk next about the value of GPR and SUM, or the values that we think that we're adding to SUM. The first thing major is this: it's safer for utility tracing. So this is a Google Street View image from a project we did in New York State. So this intersection is something we collected with GPR. This is not something you can tell. It's like 10 lanes wide. You don't want to be in this intersection. You just can't with a push cart or with an EM locator. So you either have to shut it down, which would be extremely disruptive, or you're just not going to get data there. So it's obviously safer and more effective. It's fast. So this is a picture of the tracks we collected in a day in a park on the Charles River here in Boston. So we were able to collect this whole thing in a day. It was very cold, but other than that, it was very efficient. So confirming locations is really effective for us. So it's not just about finding things that nobody knows where they are. It's also about confirming the locations on our maps with another method. So we have these legacy maps, and we want to see if the GPR actually agrees with them. And one thing we do a lot is, even if we don't find the pipe, for whatever reason, maybe it's too deep, or GPR doesn't find absolutely everything, we can at least find the trenches. We often find the trenches because they're infilled with soil that's either a little bit more or a little bit less compacted than the surrounding soil. So we're able to trace these things, and nobody's digging in these streets for exercise, right? Like there's a reason for every one of these trenches. So even if we don't know where the pipe exactly is in terms of depth, we know where it is in the plan view because we can trace the trenches.
Mhm.
So determining depths is an important thing. This is something that the EM locators really struggle with when I've used them. They're pretty good if you can find the pipe. They can trace it in a direction, but you're never going to get the depth, or not confidently anyway. It's an example of a gas pipe we were able to trace very consistent at like 4.5. Finding unknown features. This is my favorite thing that we do with the GPR. This is an example of, we talked about before, these asset owners don't always tell people where their new utilities are. This is also extremely true for universities. So this is around MIT area, and MIT will have their own, most universities will have their own utilities that they don't tell everybody else about, right? And we didn't have this on any existing map, and weren't able to find it with utility locating devices. But with the GPR, we went up and down the street and we found this extremely provocative double pipe system with this kind of 90-degree kink in the middle of the street. So this is probably, it's right on top of a steam tunnel. So this is something that we had an inkling there was something there, but we didn't know that it was going to look like this. Well, something that the GPR really adds to us there. So how do we integrate the GPR into our traditional maps? So we had bread before, so I'll introduce cheese. This is the way that I like to think about it anyway. Swiss cheese, every slice has holes in it, which are the weaknesses of the method. What we do in SUM is we try and layer all the different slices together in ways that the weaknesses augment each other, so that we get at the end kind of a nice solid block, or as close to the solid block as we can. You're never going to be perfect, right? And GPR isn't magic. We're never going to find everything with GPR, but we augment our existing methods with GPR, and we're getting something that's closer to reality than we ever were before. So we start with our legacy and existing maps. DGT has a real wealth of really old and legacy maps that really helps us. That's always the base layer kind of that we start with. And we assign quality levels to everything. So, just because it's in an old map doesn't mean we necessarily know it's there, but we at least have an inkling that something might be there. We add institutional knowledge. That's from people who've been working in these streets for even decades, like years and decades. Add the EM pipe location data. And then on top of that, we augment that with the GPR. So we can holistically kind of integrate the GPR into everything else to get a better map. So we correlate the GPR to existing utilities. So all these colors here, the red would be electric. The blue is water. You can see some pipes coming through as the depth slices go. And we'll be able to say, okay, that's our water pipe. Now we have a decent idea of the depth. But the purple is something that we didn't know. So this diagonal pipe going across the street here, that's something we had no idea of. So it's an unknown feature that now can be incorporated into future maps, future deliverables. And maybe one day we'll dig a hole there and figure out what's actually going on. This movie here, this depth slice, I kind of like it because it reminds me of archaeology. You're going to see in the middle here some pipes kind of come into view, and you'll see this pipe in the middle. You can see it rising over the pipe going up and down the street, and then diving under the one that's diagonal there over by the manhole. So you can almost put yourself in the mind of the engineers who had to say, okay, where's this pipe going to go? We got to go over this one, under this one. We can tell that some are older and some are newer. You can kind of figure out when these would have been installed, or the relative age of them anyway, and that can help even identify which ones they are if you didn't know already. Yeah, so in collaboration with traditional locating techniques, we use GPR. And remember that map I showed you before where it was just direct, it was just connecting the dots. Well, accurate width really matters. And this movie really kind of underscores that point. This is a telecom situation. I think it's fiber optic. So it would be new. Maybe we didn't know about it beforehand. But you can see how wide this is. It's not just connecting the T to the T to the T. You have to know how wide this is, because this is like 3 or 4 feet wide. And something that you really wouldn't want to hit. Some people would be really, actually here, the people whose utility this was, if you had hit it and disrupted their entire internet, they would have been pretty frustrated with you. So you got to know where the edge of this thing is. Not enough just to draw a line down the street. So I'm going to give an example now of how we mapped this street called Binney Street in Cambridge. This is just north of the MIT area in Cambridge, and how we integrated GPR into this. So we recorded it with our Kontur system. We, after filtering, used signals from 200 to 1200 megahertz. So the resolution, we had resolution near the surface and at that depth that I was happy with. In total, we had 600 features identified with the GPR. 10 feet was the deepest item, and then right at the surface, 0.2 feet. That's right at the surface was the shallowest thing we were able to see. So 200 of these out of the 600 were totally unknown. So these are unknown in the existing maps and weren't found with traditional utility locating techniques. So here's an example. We have an unmarked drain system. So we know it's a drain system because we have a catch basin at the surface, but we didn't have this. We didn't have this drain. We didn't have the depth of it, and we didn't see it diving. So we have an unmarked drain going across the street, and that's marked in purple. And we're able to tell. It's better to be able to tell this how the depth changes with the drain pipe going out to the left here from the catch basin, rather than just drawing a line between the two items. We're able to see pretty accurately where the top of it is. This is a pretty good example of how GPR alone wouldn't be enough for our purposes. So with the drain pipe, you can draw that with the GPR pretty well. But this extent to the detention system, this is not something I necessarily would have picked if we didn't know what the way that these buildings in this area were being built. So we were aware from legacy information and just institutional information that detention systems like this exist around, and we were expecting to find it. And so we can, using that knowledge, we can bring that knowledge to the data interpretation side and say, okay, well, now I think I can trace it with the GPR because I think I know what I'm looking for. Whereas if you just gave me this data blind, I would definitely be able to pick that pipe, the drain pipe going across the street, but I really wouldn't have any idea about the detention system. But because we have this information, a more holistic SUM technique, we can really improve these maps.
Yeah, that is a good point. You do need to have you're absolutely right. I mean, from the absolute beginning of your presentation, it's all about pulling together all of the sources and then multiple detection techniques, everything you can collect
that's right.
and then pull together, right? And I suppose sometimes, I don't know if you've ever found this, but sometimes you'll get clients that just won't give you that information because they want to test to see if you can find it out for yourself. So not really the best approach. It's nice to have as much as possible so you can really bring the project alive.
One thing, the interpretation that we do is we always bring our map. You can see with all this interpretation, I always have this map in the background. You can see here. Or I usually do, and that's our the map that we have before we did the GPR. So
that's your composite.
Yeah, that's our existing map with the various quality levels on it. So whether or not it's a legacy information, or maybe we traced it with an EM locator, all that information's on it, and our best guess on the depth and all that stuff.
Yeah,
So
nice. And
that
you've got the
really, I've
diameter and everything.
found, yeah, when
Mm,
I'm interpreting data without that, I think I miss a lot of things because you're just not sure. Um, you're just not sure is if it's like a rock, for example, or
yeah.
if you're expecting something to be there, and then when you see something in the GPR, you're much more likely to pick it.
Yeah,
So
absolutely. And
I
you
think
can
it's
make some
critical.
adjustments, can't you, to the visualization of the radar data, which would mean you're actively looking for something, which is very different to observing an entire data set in one way
Yes.
and picking out things that you see versus knowing that something is meant to be there and going for, and looking for it. That's a completely different approach, right?
Yeah, yeah.
I have
So
a
directed, yeah.
I have a question for you. Uh, from Joseph Reiter. Hey Joe. One of the things he's asking about is about accuracy. So accuracy in positioning your data, right? So locating utilities. So is it GPS with satellites, or is it base RTK, survey markers, those kinds of things? Since you work
Yeah.
in some open areas and some areas that are a bit more urban, high buildings and such.
Yeah, it's a really good question. It's extremely critical. The way we do it most of the time is we have RTK GPS. So we very expensive GPS systems that we hook up to the system, to the radar, to locate. And all the data that I'm showing you here was done with the GPS, and all with in highly like good fixes. When it's not as good, we have to usually get rid of that data. There are workarounds for that. So I know with the Kontur, we've used, on certain times we've done it with a total station, so a survey instrument, right, to be able to locate our data, but that can be a bit slow. So it's not as it's useful if you have a targeted location you're looking for, but most of the time we're just using a GPS. It's definitely a problem on certain streets like urban canyons, and that's something that we are addressing right now. And I'll actually at the end of this presentation, I'll show you the way that we're going to address that, or we're planning to address it in the near future. Being able to collect even when we don't have any GPS. Yeah, but
All right.
it's extremely important, because otherwise there's almost no point if you
Positioning.
positioning. If you're positioning it wrong, there's almost no point to draw the map.
Yeah, you can't identify anything, and it's useless. Which is and really the system that we built at Kontur is positioning is absolutely critical to the whole process, and I think we handle that very, very nicely, and we're incredibly flexible with it as well. So, all right.
Yeah, that's right. Actually, that's true. We've been able to when we get, well, I'll talk about it at the end, but yeah, we'll talk about the location.
Let's not ruin the surprise. If there is
Sure.
one. All right.
All right. So this is we actually see a lot of metallic plates in the street around Cambridge in Boston. So sometimes they're at the surface, when they're repairing, you'll see metal plates, but sometimes they bury them too. And this is an example where we didn't see the steam line, but we were able to see the trench, and we were able to see these shallow metal plates at only like 0.3 feet deep. So that tells you that the steam line is probably shallower than you think it is, because it's there. These metal plates are there probably to protect it. Really simple thing to find with a GPR, but kind of satisfying. I like these induction loops. So this is the traffic control induction loops that they use to control like red lights and green lights and that sort of thing. They create a loop with your car when you're sitting over top of them. And these are something that you would have to, if you wanted to dig in the street, you would probably have to remove these. So it's something certainly is useful to know about. And this tells you that even though we had been using sort of a low pass filter in the street, we're still able to see these and trace them very accurately. It's pretty shallow, so it's kind of impressed with that. So this is the last example from Binney Street that I'm going to give, and this is sort of the example that ties everything together. What we were able to find when we were collecting on Binney Street, the northern lanes, here was this series of regularly spaced pits, or these, I guess I didn't know they were pits at first. They were these rectangular features anyway. They were a series of rectangular features exactly 12 feet apart. And they were really similar in character, in size, and in depth. If you looked at them in the cross section, they were really similar. So they're related for sure, but we really weren't sure why. We didn't see any utilities or anything associated with them either. So, what are we looking for? It was kind of a mystery. But we were able to, using our existing maps and our quality level C and D data, so this is the legacy map data, these line up really well on some where we suspected there were some abandoned gas lines. So what this tells, and because we have some institutional knowledge about how these gas lines were installed and also repaired, now we know that they were repaired. Whenever you had to go in and repair these gas lines, you would make a pit every 12 feet, go down, fix the joint, and then you'd only have to do it every 12 feet rather than digging up the entire pipe, right? So now we know that the abandoned gas is still there, and we know the location of all the joints. If it wasn't still there, you wouldn't see just the pits, right? You'd see one long trench at least, because they would have to bring it up. But without all the techniques, so without including the institutional maps, without including the old knowledge, all the holistic view of the SUM, and then the GPR on top of that, we would never be able to confirm this. So now we know that there's this pipe there, and it's valuable real estate. If you wanted to build a new pipe, now you know there's an abandoned pipe there, right there, actually, because you know where the repair pits are. So dig it up, remove it, put your pipe there. It seems like it's a no-brainer. Yeah, so that's some of the value.
You could maybe insert your pipe through the previous one or whatever. I mean, you could really save.
Yeah, but it's real estate in a very valuable part of the world that would be available for you, if you wanted to use it.
Mm-hmm.
Yeah, and then the final calibration of GPR is, of course, actually digging things up, and this would never go away, because no matter how much GPR you do, you always still need to confirm things now and then. So we get this is an example of vacuum excavation, which is the typical way that we do this sort of thing. So digging a pit, vacuum excavation is non-destructive. We can uncover these utilities. We get the accurate depth, and the way we interpret GPR all the time is, you do your hyperbola fitting to get a decent estimate of your depth, but it's not perfect. It's always going to be an estimate, and it's going to be an estimate that changes throughout the street. But once you get one true depth, one place in the street, it's you can now calibrate your data throughout the entire collection point. So it really helps have more confidence in the depth estimates if you get one good.
Yeah, and this is the next. So this is the level. So we start at level. You move through the levels, right? You start at level D and level C. Level B is the actual
level B is geophysics. Level A, we're actually looking at the pipe. We're actually getting survey grade accuracy, the real true depth below the surface. So now we can say, okay, this pipe 3.5 feet is what we're looking at there on the cross section. But maybe it was only 3.3 or maybe 3. When we uncovered it. So then I can adjust the way that we process the data such that the points we know are accounted for, and that will propagate through all the rest of the data.
Absolutely. Yeah. I have a specific question from Tom here. It's about your settings for the antenna in general. So just so that everybody's aware, the array is quite flexible. So even though the antennas are they're in a line, right? So it's an array. They're stacked together to make a width. Okay, and they are fixed, of course. But your frequency of how often you take a measurement is customizable. You can choose that. You can have from a centimeter up to a meter, for instance. Okay, and everything in between. But you can also change some other parameters. For instance, time window, your dwell time. Things like this. Okay, so he's asking questions about this. So about your dwell time, your sample rate, time window, things like this. What do you tend to use?
I usually keep things. I like to keep the quality as high as possible, so that I'm driving as slow as is reasonable. Or I guess I don't want to have to drive any faster than I can. So if you know what I mean. I'm not saying that right. I have to drive as slow as possible, or as reasonable, I guess. As slow as is reasonable. So I have the quality higher than I otherwise would. Now there's a quality, I can't remember the name of it, but it's the product of the window and the dwell time that is sort of the true
integration. Integration time.
Right. Yep. And that, I think that runs linearly with the dwell time, but like it's by 2 or something with the the time window. So it's like more effective, I think, to increase the time window, even though it's a bit counterintuitive. I never
Yes.
looked into that, so that I did the math so that I could figure out what would be the most effective trade-off for this. So I keep the time window a lot longer than I actually need. The time window is like 62 nanoseconds or something like that. The dwell time, I have it not as high as I could, because increase the dwell time reduces how fast you can drive faster than increasing the time window. I like to keep I think it's at like 3.5 is the usual one I use. Of course, I can change, they're flexible based on what you want, right? Based on the needs of the project, but there's the typical ones I use. So that's the starting point. The trigger spacing, I have it at 7.6 centimeters, because my understanding is that's very similar to the channel spacing on the radar.
It's
So
exactly
it kind
the
of,
same. Yeah.
yeah, okay, perfect. So it's kind of satisfying to have that as a nice grid where the channels
Yeah,
are exactly the
square
same.
grid.
Yeah, exactly. The grid is perfectly square. It just sort of makes sense that way. It decreasing that, or I guess increasing that, will let you drive a lot faster very quickly. Is my experience. Of course, you'll miss things. You're more likely to miss things, but it depends on what you're looking for. So if you have a sense of what you're looking for in the street ahead of time, and you know you're looking for a huge pipe, you don't need a trigger every 7.6 centimeters, maybe, and you can drive quite a bit faster. But usually on these city streets, we're driving at like 12 miles an hour, which is uncomfortably slow, but not so slow that, with flashing lights, anybody's really mad. Yeah.
Great, thanks.
Yeah, so this is the thing I was mentioning. This is kind of the end of the presentation. We're talking about how we're moving forward with GPS locating in urban canyons. So we have had a few problems in certain areas of Cambridge where the GPS just isn't good enough. So the way to combat that is to either use like a total station, but that is kind of slow. Or what we're working on now is integrating a SLAM solution to our GPS navigation. So what we're trying to do is not just map the underground with the GPR, but also map above ground using LiDAR, thermal, and visual all simultaneously. So we've been working with a company to try and develop this. And we've got our above ground mapping and our underground mapping integrated together. And the above ground mapping includes a SLAM navigation solution to provide corrections to the GPS, so that even when we have really poor GPS fix, we can still locate that data later in the office. And that's something that Examiner and Kontur allows us to do, because you can upload your own navigation file later, as long as it's got the right timestamps from a typical NMEA stream. Then you can upload it later, and we've tested this a few times and it works perfectly. So we can upload it later, and even if actually here when we're collecting data, in this video we had no GPS at all. It was totally off, but we were able to upload later our fixes, and it locates it pretty accurately right in the middle of the street, or right where we need it. So that's the thing we're looking forward next.
This is becoming more and more. This is becoming more and more common. This need to collect above ground information anyway while you're moving, and then take a post-process trajectory. Take a trajectory from something else. That has better accuracy, just because it can visualize or see something and fix points as it's moving, and therefore it will back calculate the positioning.
Yeah.
And really, yeah, you're right. As soon as there's a timestamp available, our system can link to it. So we are very, very flexible in this way. So that's really nice that you're moving in this direction, because I think it's a great thing to do, because it frees you up. It means the total station is not keeping you bound to a certain range. Yeah.
Yes, exactly. The total station, even if it's working perfectly, is a relatively slow system, because you need more people. You need a whole survey crew. Yeah, this is a much better solution. This will also help us even when we have some GPS, but it's just not a perfect fix. We'll be able to get some later corrections that improve the fit.
Yeah, absolutely. Yeah, Mark Walcott's here as well. He's from IC. He said he agrees. He's using a similar SLAM solution with LiDAR as well. Yeah.
But yeah, so but that brings me to the end of the presentation, so we can just chat for a while, whatever you like.
Yeah, no, absolutely. Great presentation, Mitch. I mean, since you guys have been using our systems, we've seen, the things that you've done, the system fits with DGT so well. For lots and lots of reasons. But the history of utility mapping, the recording of where the assets are buried, and it's a challenge that will continually evolve. And it was really a huge task to keep these things updated as we keep putting things in, taking things out. It's an enormous challenge, and it's not just in the US. It's globally. It's everywhere. So it's an enormous feat. But you guys,
I imagine the problem is even worse. I know people talk about it in Italy, right? Like you can't dig a subway tunnel without hitting some ancient ruin or something, and then you can't do it anymore. So at least we don't have that problem.
You're right. Yeah. Yes, exactly that. Any more questions? I don't know if there are any more. I think we've grabbed most of them, I think. Thanks, Mark. We appreciate your comments. Yeah, really good presentation. Thank you so much for the examples. They're really useful to see. We get to see. We don't always get to see project examples as in such a way, in such a quick frequency, right? Here's this, and this is what we found. So it's really nice to see with the background story as well. Okay, if you can hand me back the reins. If there's any more questions, guys, please go ahead and fire them off. If not, we will begin to wrap up. All right. So I guess since we are pretty much finished there, no more questions coming in. I think it was a great presentation. So thanks to DGT and to Mitch once again for the presentation and for being one of our customers. It's very nice. We're very proud to have you as a user of our systems. If you have found the webinar interesting, you want to find out some more about us, then you're more than welcome to fire off technical questions and inquiries to our support channel. For sales-related inquiries, the Kontur sales team at sales@kontur.tech. We also have local Kontur sales channels, so if you have a local distributor, please get in touch with them. You can also, of course, check out our website, and please follow us on LinkedIn so you can see and keep up to date with the new stuff that we are producing. Of course, the software, hardware, all things that we are looking at every day is there to improve the experience in the industry overall. So once again, thank you very much, and thank you for joining us. We will take a small break over the summer, but we will be back in September with more webinars focusing on our customers and what they do with our products. So thank you very much, and have a great rest of the week and weekend.